Hi, my name is Fescn Nyasulu. Yeah, you know me, your 1520 lab instructor. Trying a few things. Hopefully these are helpful to your learning. So I've decided I'll try some PowerPoint PPTs. So this is my first one. All right. So let's see here. This is now about lab number 4. Let's see if I can get my screen working properly here. I'm going to start at the end because it's more fun. The part that has to do with Henry's Law. Here we are, Henry's Law. You've probably forgotten Henry's Law. Me too. It is to do with how a gas above a liquid, how it affects the concentration in the liquid phase. So in this case, consider carbon dioxide. If it's pressurized and carbon dioxide dissolves, or actually reacts a little bit with the water, and then we kind of know from experience, the greater the pressure, the more stuff you can force into the aqueous phase. So here's Henry's Law. See, I can pick up a pen here. We're learning here. So this is the concentration here. Yeah, in moles per liter, square brackets, of carbon dioxide. And we're going to consider, yeah, right there, Pepsi. Carbon dioxide in the head space up there, right? Pressurized, a lot of it dissolves, right? If we could find the pressure in the head space, pressure, atmospheres, and then the molarity of the carbon dioxide that dissolves, they're directly proportional. Write an equation, and you put a proportionality constant. Great. Our goal is to determine K, the proportionality constant. So, just a few things. Carbon dioxide, when it goes actually in solution, it actually becomes carbonic acid. But we'll ignore that for now. We just call it carbon dioxide aqueous. Back to my Pepsi. Love Pepsi. You know what happens. Get that. Get that. Then I close it. Suppose I weighed it before, and I weighed after the shake. Well, it must go down because some of the carbon dioxide escapes. Then I close in 1 or 2 seconds. All right. And then I wait. Then I put in a stir bar and gently stir. First gently, and then as you go on more and more vigorously, the carbon dioxide that's in here, that left in here, goes out. And eventually, you can get all of it out. Carbon dioxide is leaving. That must affect the mass, okay? All right. Suppose that's done, and I wait. All right, then what? Then I can fill it up with Pepsi Cola and wait. And with that, figure out the volume of the head space. And from that, if I were to measure the temperature of the Pepsi and say that is the temperature of the gas that was in there, from these measurements, and assuming we are at 1 atmosphere, at least in here, I can do the calculations for determining what the pressure of carbon dioxide is up here. And then I can do the calculations to determine the concentration of carbon dioxide aqueous. Then I can solve for K. You guys are going to do that. I hope you have fun doing it. Now I'm going to move back to the other part. Equilibrium constant for iron 3+ and thiocyanate, SCN minus. There it is. There's a reaction. It's a 1-to-1 reaction. And so you have +3 and then +2 here. Right. Determine the equilibrium constant for that reaction. Now, equilibrium constants, you've seen the numbers. Some of them are huge, some of them are very small. This one is intermediate. And so we can do it. We can measure the things that are needed to calculate the concentration. And then we're going to determine, is it endothermic or exothermic? Sign of delta H. All right, Beer's law. You kind of seen this already. Color intensity or absorbance at a particular wavelength is directly proportional to concentration. There is molar absorptivity, path length. Those don't matter right now for this case anyway. All we know is that there is a constant. So basically what we're going to do is, maybe if I go back here, this thing here, the iron thiocyanate, nice red color, pretty intense. So we can then colorimetrically, by measuring absorbance, determine the equilibrium constant. So we're going to figure out lambda max. We've done that before, back in 1510. And then do a calibration plot of absorbance versus concentration. Absorbance versus concentration, in our cuvettes, those round cuvettes. Molar absorptivity, whatever those are. Anyway, the plot should be linear. Calibration plot. Then, if we take a solution, and we don't know what it is, we don't know what the concentration is, we can measure the absorbance and then determine the concentration. So that's the idea. There it is. Again, the reaction, the red color there, and then we want this number here. So we're going to determine all these three, 1, 2, 3. Question is how? Well, consider this particular situation, and you're actually going to do this in the lab itself. 4.00 milliliters of 0.002 molar iron 3 plus. Add to that 1.50 milliliters of 0.002 molar potassium thiocyanate in a cuvette. Measure the absorbance. Comes out with this number here. Okay. It turns out you can find, because you know the volume and the concentration, you can find the moles of each of the reagents you put in. That is before the reaction. And after the reaction, the red color formation, you can measure the absorbance and find the concentration of the iron thiocyanate. How? Well, we're going to measure the absorbance. And if we have a calibration plot, then the concentration, there we got concentration, in our case, moles per liter, is equal to the absorbance minus the B in the calibration plot divided by M. Sure. So I know the concentration. But I also know the total volume of the solution. 4 plus 1. All right. So no, therefore I know the number of moles of the iron thiocyanate. From that, I can determine the number of moles of the iron 3 plus that remains. I can determine the number of moles of the thiocyanate that remains. Remember, I know the original and how much is used up. The difference is then whatever is left over. So here it is. If you assume this is A, B, and 0, and suppose you form C here, then C moles, then you can subtract here. This sort of, what do you guys call this? This table. Yeah, the table. The ice table. Forgot that. The ice table. Sure. Anyway, moving along. And so you can do these calculations, A minus C, B minus C, and then if you divide it by the total volume, then you can find the volume in liter, then you can find the concentration of each one of these, and then you can calculate the equilibrium constant. So procedure, as you've done before, determine lambda max. Make a little of this red solution, measure the absorbance at all 4 wavelengths, and determine which one is most absorbing. And then use that wavelength for the calibration plot. Now, here's where we are pretty sophisticated and make things easy for you. So here's how we do it. iron thiocyanate react. It turns out the equilibrium is not too big. It's sort of 100-ish, 100, 200, thereabouts. We want to do a calibration plot, which means we must know the concentration of the iron thiocyanate so we can measure its absorbance. But we're doing it via a reaction. How do you do that? Well, just react a whole huge excess of iron 3 plus with a controlled minimal amount of the thiocyanate. Under those situations, the reaction practically goes to the right hand side, or the reaction is complete, and then we can know then the number of moles of the iron thiocyanate that's formed. How do we do this here? This is how. 4 milliliters in a cuvette of 0.200 molar iron 3 plus. React that with 0.1 milliliter increments of 0.002 molar thiocyanate. Huge iron. So, based on the moles of the thiocyanate, assuming we push the equilibrium complete to the other side in this case, we can calculate the moles of the iron thiocyanate that's formed and then determine its concentration. So, practically easy. Most people don't do this. They make different solutions. Formulas. Iron 0.2 mole iron 3 plus, add 0.1 milliliters of 0.002 molar potassium thiocyanate in a cuvette. So don't remove the cuvette from the absorbance measuring system. Let's go. Then put it on a stirrer, over the stirrer. Let go right. Then like that. Then measure the absorbance. Another 0.1 milliliter 100 milliliter increment. Stay it a little. Let it settle down. Measure the absorbance. Continue doing that until you've added 10 or so, or until the absorbance is 1.5. Stop around then. You'll have an Excel sheet. You'll be able to calculate the concentrations of the product, Fescn, based on the number of moles of the thiocyanate that you actually added. Hi, here's my calibration plot. Pretty good, pretty good. 0.9995 R squared. That means it's pretty good. All right. That's our calibration plot. Now, equilibrium solutions. We got this. We'll do things that make sense and make us get a lot of meaningful data. So, here's how. Now, equilibrium, you'll note that in the case of equilibrium, 0.002, 0.002. So we sort of, the two of them are about equal. They don't have to be 0.002, it could be 0.00, 0.001, but they're about equal. And so in this case, 4 milliliters in a cuvette. Put it in of the iron 3 plus. Add 0.50 milliliters of this. Stir, measure the absorbance. Add another, stir, measure the absorbance. Continue until the cuvette is full. You should have dried your cuvettes, otherwise you end up with the thing filling up before you get to the end. And of course, in this case, very important to operate the autopipetters correctly. You can check that your autopipetter is working properly by, before all of this, trying to weigh water. Should get the densities of pretty close to 1. All right. Operate your autopipettas properly so you can get good, appropriate data. So the 5 equilibrium solutions here, they're all different. And then we measure the absorbance. And then we roll over and keep this constant 4 milliliters, and we vary these. So we have 10 equilibrium solutions for which we can find 10 equilibrium constants. We can look at the values. If this concept of equilibrium constant really holds, they should be reasonably constant with some little deviation as calculated by the standard deviation. So that's what we're going to do. And then you get your Excel, do the calculations as indicated in the ICE table, look at your constants, and come up with the equilibrium constant for that reaction. How about sine of delta H? Well, you know how to do this. Le Chatelier's principle. Take one of the solutions, split it into 2 for comparison's sake, right? Put it in an ice bath. You're lowering the temperature, and see whether the red color intensifies or not. Based on that, be able to, by applying Le Chatelier's principle, be able to say whether the reaction requires energy or produces energy. Now let me ask you this. Given what we did in lab number 2, intermolecular forces, given what we talked about there in terms of bonding, what are your expectations? All right. That's our lab for this week. Let's see. Yeah, that's our lab for this week. I hope these presentations were useful. If they are, I'll continue. And so I'll be checking with you sometime this week to see if you found them useful or not. Have a great day, everyone.